Well, I'm sorry I can't really be with you, but I do want to say something about Dr. Robert Byer and AFOSR. I want to extend my appreciation to the AFOSR for its generous support of my own research through the years, especially those early years when the funding helped support my maser and laser research activities. I dare say that we have both come a long way since then, although I don't know which of us is worse off for the wear. 60 years can be considered a lifetime for many people, but for basic research it is rightly considered part of the foundational research we need as we move ahead making new discoveries. Basic research is a key to how good the future will be, and the Air Force will continue to play a role in that, especially ensuring that the United States Air Force maintain its preeminent role in air and space. And one individual who has helped in that regard is Dr. Robert Byer, who hails from a very modest research facility. We call it modest here, called Stanford. I can think of no one better to address you today than Bob Byer, who has made numerous contributions to laser science and technology. In closing, I extend a happy 60th birthday to the Air Force Office of Science Research and wish you many more decades of success. And now, as to Bob Byer.
Let me say that having Charlie introduce this talk was beyond my wildest imagination. So I think we all owe Charlie a little note saying thank you for making the video and helping us kick off a speaker series on the 60th anniversary of AFOSR. AFOSR played an absolutely crucial role in my technical career, and that's because early in the laser days, we had this marvelous tool, this instrument, this coherent light source, but we didn't know what to do with it. We had no clue what the laser could do for us. And Art Challow called it a solution in search of a problem. And so I'm going to try today to show you from a 50-year perspective, which we celebrated last year, that the laser has found solutions. In fact, many more solutions than most of us realize. So I hope to surprise you a little bit by some of the ways that lasers can be used, in particular ways they can be used to support the mission of the Air Force. So, to look back at the days of the laser and nonlinear optics, by the way, lasers were celebrated last year in a major event called Laser Fest. More than 1 billion people around the world took part in Laser Fest over the 1-year period. I made 6 trips to Europe during that year to give talks. So my mileage plus miles are doing really well. And this year we're celebrating the 50th year of nonlinear optics, which is the heart of my field. And so I didn't feel too old last year with 50 years of lasers, but this year I'm beginning to feel it because my own field is 50 years old. Something else is going on. So we'll talk about Air Force-sponsored research in lasers, but I'm not going to give you any list at all of projects that the Air Force has funded. You're going to have to surmise that from what we hear. All right, Charlie, Making Waves. So I recommended my graduate students that they read this book, Making Waves. And that's because Charlie has had an eminently successful career, and he really is a model for all of us in combining service to the community, to the Department of Defense, to his university, with a research career that continues even to this day. The photograph on the lower part of Francis and Charlie was taken last year at Laser Fest in San Jose. Of course, the laser kicked it all off, and the first laser was built by a former graduate student from Stanford at Hughes Research Labs, and that was built on May 11th, 50 years ago last year, a ruby laser, a flash lamp pumped chromium-doped sapphire crystal. And so the good news is many of the people on this screen are still alive, but others have passed on, and lasers at 50 was quite a celebration. The celebration for nonlinear optics at 50 wasn't quite so extensive. All of us in the field decided that we would meet in Hawaii on the island of Kauai and celebrate 50th anniversary. So this is a photograph of Peter Franken. He first put a ruby laser through a crystal of quartz and generated a tiny bit of blue light, the second harmonic of the ruby frequency, and submitted the paper for publication in FISRA Letters. And of course, like all really good novel papers, it was rejected. He went back and wrote again, and told the editor that it was really important, this was really a novel thing, and the editors decided to publish it, but not until they had cleaned up the image and erased the smudge that was on the image, which was the second harmonic generated light. So I tell my students, doing the science is the first thing, writing the paper is the second, but you have to get it published. Don't be discouraged. Often the hardest part is getting the results published. Peter became a good friend, and over the years gave me really good advice in my younger years as a faculty member. All right, so early advances in lasers and nonlinear optics with Ted Maiman in 1960, kicking the ball down the road. I'm going to talk a little bit about Earl Bell at Spectrophysics, where I worked for a year, and the Argon laser. Steve Harris, who was my thesis advisor, every Wednesday. And I asked my boss at Spectrophysics, Herb White, could I ride my bicycle from Mountain View up to Stanford and attend Tony's brown bag lunches just to learn what's going on at Stanford. And he said, yes, I could do that as long as I made up my hours later. Good president, get your work. So this is John Bjorkholm, one of Tony's first students and the first applied physics student at Stanford. This was taken a couple of years ago at Tony. And so I attended these seminars, and I learned about words called nonlinear optics and second harmonic generation from Tony and his graduate students. And that led me to then apply for admission to Stanford as a graduate student after working at Spectrophysics for a year. But I'm going to pause here a minute and just inform you, if you haven't heard already, the unfortunate news that Tony passed away a few weeks ago. It was sudden and unexpected. He was in good health. And all of us remember him as really an example of what Steve said. He's a shining example of what a scientist should be. He was very personable, very helpful, went out of his way to help people that worked with him and around him. Steve Harris. So I was accepted at Stanford. To this day, I can't figure out why. And I was assigned to work with a young assistant professor, a first-year assistant professor called Stephen E. Harris. And Steve said, we're going to do nonlinear optics. And I attended Sony's seminar. I knew what the words at least stood for. And I'd read Bloombergen's book and Boyd and Ashkin from Bell Labs. And Steve then said, the goal of our work is to build a tunable laser source. And we need a nonlinear crystal. Since Steve came from Bell Labs, he called his friends at Bell Labs, and they sent out 1 cubic centimeter of the most beautiful lithium niobate crystal that I'd ever seen. That was my thesis. Well, we're working with this crystal and getting some things done, and oops, we dropped the crystal. Now, the carpet on the Instant Lab is called concrete. So the crystal hit the carpet of concrete, splattered, and split into a million pieces, and there went my thesis. So I thought, now what do? Well, you look around. Later, I worked with a scientist from Russia, Lev Kulevsky, and he told me the path to physics is neither paved nor well marked. Well, it also is filled with lots of accidents. So we had an accident. What do? Well, it turned out we contacted another professor, a young professor in the material science department, Bob Feigelson, and asked Bob if he could help us grow lithium niobate at Stanford. And the answer was he could, and he did. And within a year, he'd prepared the first niobate crystals at Stanford, and he'd improved them substantially over what Bell Labs had done. So we had better quality lithium niobate than Bell Labs was able to produce. And working with Bob, we were able to get the niobate to the quality and the length required for my thesis work. Marty Fayer later went on to help us take a Bloombergen idea called quasi-phase matching, apply it to lithium niobate, and now quasi-phase matching, a new way to do nonlinear optics, has been widespread use. But working with Bob over the last 30 years, we went through a whole host of infrared nonlinear materials and other visible materials, and many of these were transferred into the commercial stream and are now available as nonlinear materials for your experiments. So here's a lithium niobate boule, a boule of KDP. I mark out the KDP because this particular crystal of KDP was purchased for $10 from the War Surplus store on Colorado Street in Pasadena, California. Why would Pasadena, California War Surplus have KDP crystals? They would because those were the piezoelectric crystals in the submarines in World War II. And that's exactly the crystal class that we needed for nonlinear optics. So my goal is keep track of the KDP. It will come up a couple more times in this talk. Steve Harris. So Steve says, okay, our goal is to build a tunable laser, a parametric oscillator. and we had nonlinear materials, but we didn't have all of the things we needed to make sure the OPO was going to work. And Steve, in his wisdom, said, okay, look, let's first look at the noise from a parametric amplifier called parametric fluorescence. We will use that to measure the nonlinear coefficient, the parametric gain, the parametric tuning, and then we'll build the oscillator. And it turned out it was a very wise step. We went ahead and looked at the noise. The image here isn't quite as good as it should be, but we reproduced this experiment a couple of years ago for Steve and for his class. It's very easy to see the parametric fluorescence from a tunable parametric oscillator. Important discovery. Turned out now it's in widespread use in quantum optics and quantum physics. So how do we build an OPO? We started with an argon ion laser. Spectrophysics helped me to design and build that one. We put the crystal in the oven to keep it at a temperature where it would phase match properly, and we pumped with all the power we had, and it turned out the threshold for this device was 430 milliwatts of green light from the argon ion laser, and we had available about 470 milliwatts of green light. We were barely above threshold, but there's a little bit of red light showing in this picture right there, so we had the first tunable visible laser operating, and Steve was really excited. So he said, let's invite our wives to come in tomorrow on Sunday before we go down and give a post-deadline paper at the Quantum Electronics Conference in Miami Beach. So we invited our wives to come in. Fran Harris came in, and my wife Evie came in. We turned on the argon laser, which is quite a feat. It's a big machine. And we get the OPO above threshold. We get a little bit of red light. And my wife's looking at this and says, is that all there is? So, first red light, tunable source. It went commercial in a company called Chromatics. They were the first to make a tunable parametric oscillator as a product. It turned out later that product was reproduced by Spectrophysics in the 1990s and became really quite an important product area. This is a picture of a very young Richard Wallace with a Q-switch YAG laser, which is pumping this parametric oscillator, which is tunable. All right, so here's a little bit of the early history of laser companies in the Silicon Valley area. Spectrophysics was the first company. Chromatics spun out of that because Bob Rempel had started with Spectrophysics. Now he's a new company. Coherent spun out of it because Jim Hobart had started at Spectrophysics. So his was a spin out. And these two companies had people that started a little company called Quantaray that I got involved with a couple of decades later. All right, so little companies are getting started. The laser business is starting to get some traction. Scientific applications of lasers. So our motivation at Stanford in doing research and in developing lasers was always driven by a scientific application. We didn't invent lasers unless we had a need and we had a goal of what we needed to build in the laser technology area. And the early motivation for our work was atmospheric remote sensing, which involved laser spectroscopy in the infrared, and a transmitter. We needed to build a relatively big laser transmitter. And then we ran into Milton Huffaker and learned about global wind sensing. And I learned from consulting with the Air Force at that time that the measurement of wind was really quite important, especially in the arenas in which you can have operations in battlefields. So this was our first goal. Our second goal came a little later, global wind sensing. Well, my first PhD student was Helge Kildal from Norway, from Oslo, Norway. And so we first wrote a paper on using tunable lasers, the parametric oscillator, to measure the spectrum of molecules in the atmosphere and then transmit laser beams in the atmosphere to do remote sensing of those pollutant molecules. This is an absorption spectrum of a carbon monoxide molecule taken with a parametric oscillator. And so these tunable sources were useful for identifying elements in the atmosphere, molecules in the atmosphere, the pressure and the temperature of the atmosphere remotely. It turned out that remote sensing was an international affair, and Sune Svanberg from Sweden was working in the area. The late Herbert Walter in Germany had an effort in the area. And in my first trip to Japan, I got to meet Professor Fumio Inaba and his students who were also working in laser remote sensing. So here was a scientific drive and application that had gone global already in 1974, and a number of people were involved in this research. And for me, it was an eye-opener because I could travel to Europe and meet with top scientists. I could travel to Japan and meet with top scientists, and together collaborate in doing research without these boundaries getting in the way. So we were successful in measuring methane and SO2 and water vapor and atmospheric temperature, all using a laser, a YAG laser transmitter called a quantum ray laser today as our transmitter. So how did we invent the laser that drove the parametric oscillator? We went back to the source. Here's our telescope on top of the Ginston lab at the time, and we had a tunable source based on lithium niobate, and that tunable source was computer controlled. This was the first time a computer was actually used to tune a laser. It was a PDP-11 computer. It didn't have the 8K of core memory, 8K of core memory. But it worked, and we were able to scan this continuously in the infrared. So here's how we designed the laser. We went back to the source of all knowledge of lasers, Tony Siegman, and he had invented a laser called the unstable resonator laser in 1965. And it had been tried. People had tried to build the unstable resonator in solid-state lasers, but they had failed. And if you read the textbooks at the time on lasers, it would say, the unstable resonator works fine for gas lasers, but it doesn't work well for solid-state lasers. Well, that comment turned out to be quite important in getting a patent on the unstable resonator applied to solid-state lasers. So Dick Herbst, my postdoc at the time, Hiroshi Komiya, graduate student at the time, and I sat down and thought about how we could build an unstable resonator in YAG that would allow us to get more power and more energy. And we fabricated this piece of optics in the Ginston Optical Fab Shop. We set up the experiment on a Friday afternoon, and within 5 minutes we had made a 200 millijoule diffraction-limited Q-switch YAG oscillator, more than an order of magnitude increase in energy compared to a regular stable resonator lasers. Siegman was right. If you did the unstable resonator correctly, you could get a very, very good laser performance. So this laser led to commercialization in a company called Quantaray. And Quantaray was founded by Earl Bell, the same Earl Bell at Spectrophysics. Why did Earl Bell want to start another company? It turned out his hobby was trains. Now, not model trains. His hobby was full-scale narrow-gauge railroads. He ran a railroad called the Chama Toltec Railroad in northern New Mexico. You could go down in the spring and you could ride on these trains as they pulled it up the gorge up there, and Earl had run out of money. Running big full-scale trains costs a lot of money. So what do? You go start another laser company and make another $1 million to continue to run your railroad. So that's what Earl did. So we provided him with a laser source that would be the basis for this company called Quantum. And so there's what the laser looks like. It's still being sold today. When it was invented, and we sold the first one to Germany in 1975, I made an estimate that the world would probably buy about 75 quantum ray lasers. That would probably saturate the world market. I went back in 1995, 15 years ago, and asked the president of Quantum Ray at that time how many lasers had been sold. And by 1995, more than 10,000 quantum ray lasers were around the world. That's about $1 billion worth of this laser technology. Way beyond my wildest dreams that this laser would be so successful. It's still manufactured today in basically the same form and still sold widely. It is now used to pump a parametric oscillator. And the oscillator is made out of the crystal BBO, beta barium borate, which was imported from China. All right, nonlinear crystals. So we nonlinear frequency, double, triple, and quadruple this YAG laser, and there are the KDP crystals that do the doubling. Second time you've seen KDP in this talk. It was a great company to work for. The company was quite successful. It was so successful that the employees of this company held annual parties even after the company was sold to Spectrophysics. And this is a cup talking about an era ends, the excellence continues. And so it was fun to see their friends that worked in this company for so long. About that time, I met Milton Huffaker. And Milton had a dream. And his dream was to fly lasers in a satellite orbiting the Earth and use this laser to measure the wind velocity in the atmosphere. And we knew that this laser would have to be reliable, it would have to be efficient, it would have to have average power of about 100 watts in order to transmit and backscatter light from dust in the atmosphere to measure the wind velocity by the Doppler shift off the atmosphere. Quite a dream. Milton started a company to pursue this dream called Coherent Technologies, located in Boulder, Colorado. we decided to take on this challenge. There was a good challenge. How do we do global wind sensing? Well, what it really meant is we needed to have a laser oscillator, an amplifier, and do coherent laser radar. That's what we had to do. So we started off trying to think, how can we make a single frequency local oscillator for this radar application? And that led to an invention with these authors, Tom Kane, Bing-Kung Cho, and Jeff Dixon. Bing-Kung Cho was a visitor from Tsinghua University in China, and he was one of the first scientists to come to the U.S. from China. Later in his career, he became the president of the Optical Society in China and served as president of the Chinese Academy of Scientists. In other words, this young, very quiet man who was at Stanford for a year became an absolutely significant scientist in China. It's nice to have a first author on a paper that ends up being somewhat referenced. All right, so we made a coherent laser radar in our lab. We actually measured wind velocity from the laboratory, transmitting laser radiation into the atmosphere. And what started out as just basic research in a university lab is now a very well-developed technology. Laser radar and hyperspectral analysis and 3D imaging with lasers is now the kind of technology that's used very widely and very successfully. All right, so the nonlinear ring oscillator, this little 10 milliwatt to 100 milliwatt chip of YAG, it's a small crystal of YAG, can also be frequency doubled. But it wasn't clear how you would double the diode pump laser at low power that we had at that time. And so, I know, I was going to give you an example. Oh, the unexpected outcomes. So here's an example of the unexpected outcomes. Okay, so we did this work because we were motivated by a scientific application, global wind sensing. Where is the unstable resonant? Where is this non-planar ring oscillator used today? So where are the applications? The invention motivated by science, where are the applications? Here's one that's interesting. Peter Lorraine from General Electric contacted me about a decade ago. He said, Byer, I have a real problem. We need to measure the composite panels that get installed on the Joint Strike Fighter during the process of building that aircraft. He says, it's going very slowly. It takes way too long to measure the quality of these composite panels. Can you help us out? So I traveled to Fort Worth, we looked at the setup, and we realized that we had the laser that he needed. The non-planar ring oscillator with this very narrow line width and very low phase noise was exactly what Peter needed to do the scanning, the 2D scanning of these composite panels that get then put on the wings and the body of the aircraft. We more than doubled the production rate of that aircraft through making this process a less costly and more quick way to measure these panels. The NPRO finds its way into U.S. submarines. Every U.S. submarine in the submarine fleet today has more than 30 of these lasers installed on the submarine. Why would a submarine need non-planar ring oscillators? These are the lasers that illuminate the fiber that trails behind the submarine that makes incredibly sensitive sonar detectors, both angular sensing and distance sensing. The NPRO, of course, is used in science, and it's the laser that is at the heart of the gravitational wave detection project called LIGO, which has kept us busy for the last 15 years. Our goal is to see gravitational waves in the universe sometime late this decade. Green. All right. So Bloomberg taught us we could do nonlinear optics. We've been doing nonlinear optics. A student asked a question in class, and the question he asked in class is the following. Professor Byer, can we frequency double a CW diode YAG laser with good efficiency? At that time, we had milliwatts of output power from our diode pump lasers, and that was a question by Jeff Dixon. My answer in class was, I don't know. If you go home and do the calculations, I'll go do the calculations. I'll meet you in class on Tuesday and let's compare notes. Within the following Friday, we had put a nonlinear crystal inside of a diode pump YAG and doubled and made green. We then wrote up a patent application. The patent was eventually issued to Stanford in 1986. And I write down in the bottom line, it's my favorite patent for two reasons. One, because it was motivated by teaching, by a student in class asking a question. And two, it's the most widespread sort of use of a laser by amateur astronomers. And I'm an amateur astronomer. I love this green laser pointer because I can give shows on a Saturday to the public and I can point to objects in the sky and you see the backscattering from the green laser coming back, and it's really easy to point out the Andromeda galaxy to someone who doesn't know where to look in the sky. So, green lasers found a number of applications. The patent ran its course after 20 years, so it matured. in 2006, just before green laser pointers became a market success, right? So now we're going to look at this picture because Stanford takes its patents very seriously, so we need to do a transition. Here we go.
Faculty at Stanford University continually develop world-changing ideas across all disciplines, among them the laser. This cutting-edge creation harnessed the power of light and has since helped advance everything from modern medicine to manufacturing. And even now, over 40 years later, the laser's full potential has yet to be realized. Hail, Stanford, hail.
Okay, you should have some fun with that, right? Every time I watch that, there's a moment in that slide where the cat bangs its head into the wall, and you wince when the cat goes bang. All right, so we do take our patents seriously in the Stanford sense. That is, we have fun doing the research and also writing out the patents. The green laser pointer is a useful tool. It's actually the application I found that really interested me is it's used to rescue sailors at sea. That is, a 100 milliwatt green laser pointer in a flotation with batteries shines up into the sky and illuminates clouds overhead. And if you're in an aircraft looking for someone lost, you can see the green laser pointer illuminating a cloud from a long way away. And you can follow the green beam right back down to the source. So I would have never guessed that a green laser pointer would have that kind of application. So now this is a view of the Bay Area laser companies in 1984. That's 20 years after Spectrophysics was founded. Lightwave Electronics is the first company to make products in diode solid-state lasers. Coherent Technology, founded the same year by Milton Huffaker, making lasers for wind sensing, aircraft takeoff and landing, and radar. New Focus, Milton Chang moved up to Northern California from Southern California and builds a whole set of new tunable lasers with diodes. Spectre Diode Labs, a joint company between Spectrophysics and Xerox, founded in 1983, begins to build diode lasers for various applications. We have national laboratories in the area. We have companies that reach across the world now. That is, lasers are being made in Europe. They're being made in Japan. You're beginning to see this field is maturing. It's starting to grow. So here's photographs of Tom Kane and Bob Mortensen, the CEO of Lightwave. Milton Chang and Bob. Milton came up from Southern California, as I said. Lightwave made precise light for manufacturing semiconductors and electronic circuits. Here's some other Stanford graduates. John Willison went off to start a company called Stanford Research Systems. He took HP on head on. He built instruments that competed directly with Hewlett Packard instrumentation. Here's a nice love story. Kurt Weingartner and Ursi met at the Ginsten Lab when they were graduate students, got married, moved to Switzerland. Kurt runs a company called Time Bandwidth Product. Ursi publishes more optics letter papers than anybody in the world in any given year. She does an amazing research job in lasers at ETH in Zurich. And a year ago, on the 50th anniversary of the laser, we held a reunion of all the graduate students out of the Ginsten Lab who would show up. And we've graduated about 250 PhDs since 1957. And this is about I think a fourth of that number sitting here in this picture, the number of former students that came back. This building and its courtyard and the place we did research for more than 50 years is now gone. And we're building new engineering and science buildings on this part of the campus. Now I'm going to move into a different direction. Commercial applications of lasers. And I'm going to introduce you to an idea that the laser is a stealth utility. Now, the Air Force has been responsible for another stealth utility that impacts all of us in the world. And you might think about it a little bit. It goes by the initials GPS. All right? So GPS was made for military applications in mind. In fact, the Department of Defense did everything they could to prevent the public from using it by modulating the frequency and things. But in fact, GPS is a utility. It's now in demand. We all use it every day. We don't even think about it being there. So that's a stealth utility. And I borrowed this term from the Air Force major who helped to lead the GPS effort to success. And so the laser is also a stealth utility. It's in your life in many ways. You just don't see it and don't notice it. So we did an exercise last year on celebrating a laser. What would happen if all lasers in the world suddenly stopped right now? Well, the first thing that would happen is all the lights would go off. Second thing that would happen is all communication would go to zero, right? Why would the lights go off? Because all the timing that runs the generators that makes the grid work all disappeared. So there's all kinds of ways that lasers would stop the world from working if they didn't continue to work and do what they should do. But the question this morning I should answer is, what applications of lasers best serve the Air Force? How do lasers meet the Air Force needs? So we'll answer that question, and we're going to look at a few of examples in these kinds of applications of lasers. And one of those is the laser eraser. Here's the laser eraser called laser ablation. And you're going to find that there are applications for laser ablation that are really quite important for the United States Air Force. All right, so in 1984, we built a 1.5 milliwatt laser, 1.5 milliwatts pumped by an 8 milliwatt diode laser. The question right now we're going to explore is, how did we progress from this milliwatt laser in 1984 to a 100 kilowatt laser in 2009? 100 kilowatt diode pumped solid state laser in 2009. How could this happen that you could make that kind of progress? So that's what we're going to explore for a few minutes, and then we'll come back and look at applications. Okay, first innovation, diode lasers. At Xerox Palo Alto Research Park, Don Cyphers, Ralph Burnham, and Bill Stryker built the first 1 centimeter wide diode laser bar. This was the first high-power diode laser at room temperature. It operated with 25% electrical efficiency, and the 1 centimeter bar created 1 watt of output power. That was a huge step forward from the milliwatts that we had before. So now we're 30 years later, in 2010, that same 1 centimeter wide bar produces a 100 watt average output power at 70% electrical efficiency. It is by far the most efficient way to convert electricity into light frequency that we have. Now, 100 watts is being actually a little calm, because in the laboratory the lasers generate more than 500 watts of average output power from a 1 centimeter bar. So the world is changing in some dramatic ways because of this solid state invention. So this is my early plot. Here's the cost per watt of the laser coming down exponentially. Here's the power per bar of the commercial lasers going up. And I showed this plot in 2008 at a Clio invited talk, and here's 2000, so it's just after 2000 maybe 3 or 4. All right, so this is sort of a version of Moore's Law. We're making more product, we're learning on a learning curve, and lasers are coming down because the volume of manufacturing is going up. So here's that slide in today's world. So this is a slide that says learning curve from LL, but this slide of the cost of the laser diodes is versus the number of bars you manufacture. And this was a slide I got from the manufacturers in Japan. So here we were way back, and when my slide was made, we were way back up here, $1,000. It's 1,000 cents per watt, and then we come down. And so the goal is to get down to about 1 penny per watt of output power from a diode bar. That's $0.01 per watt. So a 100 watt bar will cost you $1. That's the chip, the cost of the chip. The hard part isn't the cost of the chip. You can make 100 million chips a year and do this, but you have to learn how to automate the manufacturing. You have to build them in arrays so that you can pump your lasers. And at the same time that this cost is coming down and the volume is growing, the efficiency has gone from 50 to 70%, and the peak efficiency occurs at a wavelength that's perfect for pumping solid-state lasers. So it's this technology that's revolutionizing the laser industry. When Lightwave was started as a company in 1984, diode pumped solid-state lasers had 0% of the laser market. Today, solid-state diode pumped solid-state lasers represent 1/3 of the total laser market, and it's growing. All right, so Ellen DeVosela, this is for you. So Ellen's in the audience. Here's a program to build a 1 kilowatt diode pumped solid-state laser called the DAPKIL program. and it was at TRW, now no longer called TRW. A very, very difficult laser to build, 10 joules of stored energy, 100 hertz repetition rate, near diffraction limited, double to the green. And these were diode bars that were just being made at the time, pumping a zigzag slab solid-state laser. Our work at Stanford at the same time, we were thrilled to build a 40-watt TEM00 mode laser pumped by diodes. The diodes that we used cost us $280,000 to get 40 watts of output power. My wife heard that number and was just astonished. She said, I could buy 10 Porsches for that amount of money. So it was not a very efficient way to go, but it was promising. And so when things look like they have a path forward, you pursue them. All right. A few years later, working with a graduate student, Todd Rutherford, we realized if we pumped the slabs not on the face, which is the traditional way, but we pumped on the edge, called it edge pump conduction-cooled slab lasers, we could scale the slab laser power to hundreds of kilowatts. Hundreds of kilowatts. We originally submitted the paper with the title, A Megawatt Average Power Solid-State Laser, and that got rejected. Not by the reviewers, but by the DOD, who said we couldn't publish the words megawatt and solid-state laser in a single sentence. That was unknown to us, but we retitled the paper 100 kilowatt. That's okay. At that time, I was invited to go to Albuquerque and meet with the Air Force Research Labs, and I carried with me some pieces of plastic that were this size, that were so long, 30 centimeters long, 15 centimeters high, and I asked 3 generals in the audience how much average power could that piece of plastic generate if it were made out of the YAG and diode pump. And they guessed about 100 watts, and I pointed out it was a 100 kilowatt laser in a volume about this big. Without any new engineering, we're going to apply what we already know on how to build lasers. So that made an impression, and over time lasers have marched up this power curve, and now it's possible to build these 100 kilowatt average power lasers. The hard part is material science. It's hard to buy crystals that are large enough, single crystals that are large enough to do this. So we needed a breakthrough in material science. That came from Japan. And in Japan they realized they could grow polycrystalline laser materials, we call them ceramics, that would be low loss and that would allow lasers to scale in power. So using ceramic materials, we have a pathway forward to very high average power lasers. So the Air Force was involved. So here's an Air Force-sponsored international program on a ceramic research effort to build better laser gain materials in ceramics. And this is Howie Schlossberg in the middle. We're in the Japan Fine Ceramic Institute in Japan. I'm in the background here, and my colleague Rama Galmea is right there. And so this work helped us jointly with our Japanese colleagues to advance the state-of-the-art of ceramic gain media. And here's Rama again. So these are ceramic materials prepared at Stanford, and only this week Rama has moved from Stanford to a full professor position at the University of Central Florida, where he will carry on the ceramic research program and continue to improve these materials. So what's important about ceramics? First of all, they can be made arbitrarily large in size. Secondly, you can engineer them. You can engineer the doping profile. You can engineer the index refraction profile. Our calculations show that I can improve the laser efficiency by a factor of about 1/3 more efficiency if I build the laser from engineered ceramics and not just ordinary crystals grown from the melt. So there's a real promise here in the future. And ceramics were used to build the laser at Northrop Grumman, the 100 kilowatt laser, 105 kilowatts CW output, M squared of 1.5. It operated on January 5th, 2009. I was down there for the weekend to watch and test it. Having 105 kilowatt in the building with you is frightening. We joked a little bit that the safety officer's office was about 4 walls away, but a 105 kilowatt laser would not be stopped by building walls. Believe me, you go right through them. So the laser operates, and it operates reliably. It has now been moved from a laboratory environment to an outdoor environment where you can now transmit this 1 micron beam through optics and into the atmosphere. I like to quote here from Colonel James Jaworski, the solid-state lasers are the wave of the future. I think that's way or wave. They will eventually generate megawatts. So he's even more optimistic than I am. All right, so how do you get to megawatts? Here's our Livingston plot. This is a semi-log plot versus year of laser power. These are all research lasers. Here is the work at TRW Dapkill, starting there, the 25 kilowatt, the 100 kilowatt. And if I just go on up my semi-log plot somewhere in mid-decade, 2015, if we're doing our homework right, we should be able to build the first 1 megawatt average power laser that's diode pumped, ceramic-based solid-state laser. And a megawatt is a pretty important number. So why should you be interested in a megawatt average power? You should be interested because the warfighter would like to have photon weapons. He'd like to have a way to cut metal at a distance. And a megawatt laser easily protects from incoming objects an area that's 10 by 10 kilometers square. And that was known in a study done for the U.S. Army about 4 years ago. So a megawatt is sort of the magic number. It tells you have a way to knock down incoming artillery, mortar shells, or missiles if you have a megawatt laser in surrounding your base. Why am I interested in a megawatt? I'm interested because we've been working for 20 years on laser accelerators for doing TeV scale physics and for generating coherent X-rays. And I'll talk about that if we have time in a minute. To build a laser accelerator to do TeV scale physics, I need 10 megawatts of average laser power per kilometer of accelerator structure. So I'm talking about megawatts for a scientific reason, and that's what motivates us for looking at lasers of this scale. At the same time, my colleagues across the bay are interested in megawatts for a completely different reason. They want to build a laser fusion energy source and using a NIF-like laser, and they need a drive average power of 35 megawatt average power laser to drive a laser fusion energy plant that produces 1 gigawatt of electricity. So for 35 megawatts of power, I get 1,000 megawatts of electricity at the output using the fusion process. This is truly a nonlinear phenomenon. I hope we have time to go through and discuss it. I think we can get there. So there are reasons why we're thinking about megawatts these days, and it's quite interesting. All right, so my question for the Air Force is, the path to directed energy weapons might not be a direct path. It might be an indirect path through the commercial use of diode pumped solid-state lasers. And why do I say that? That's because the cost of these lasers has to be affordable. And if you're going to be affordable, you have to have volume of production of the diode pump sources. And until you get volume production, you're not going to get the cost down to where you can build directed energy weapons. So I'm going to give you some ideas of ways that lasers can be used in service of the Air Force that can help build the volume of use of lasers so that the cost continues to come down. All right, so we're back to the stealth utility again. I need to show you, of course, this is what you all dream about if you're a warfighter. You've got your photon torpedoes from your local ship, and you can cut this metal at a big distance. And, of course, your photon torpedoes travel at Mach 300,000, the speed of light, so the guy on the other end has a real tough time dodging that bullet coming at him. All right, so lasers. Lasers can be used in a utility sense. Lasers cut and weld. In fact, every automobile that you get in and drive in is made today with 20 different kinds of lasers in the manufacturing process. Lasers cut glass, ceramics, metal, semiconductors. Every one of these things you carry in your pocket could not be made without the laser. The laser does all the via drilling, all the semiconductor trimming, all the glass cutting, all of that's done with a laser. Laser sintering of new materials. We have new ways to make things. My colleague at Stanford calls them impossible objects. I can make three-dimensional objects out of glass, out of ceramics, out of alloys, and they can be hollow and they can have internal gears. So I can make impossible objects layer by sintering with a laser. Lasers strengthen materials. You don't know it, but every jet airplane you get in today, its jet engine blades, so turbine blades, have been strengthened by a laser. They have been laser peened. And so laser peening of jet engine blades has improved the performance of the jet engine significantly. Lasers are now being used to harden the leading edges of wings of aircraft. I'll give an example in a minute. And then we get to the laser eraser of our shallow. Laser depainting of aircraft for inspection, 2 years ago, the FAA certified that all aluminum-skinned aircraft can now be laser depainted because you don't harm the aluminum underneath the paint. Lasers can remove sealant in the fuel tanks of aircraft wings. The Air Force needs this badly. You have a number of aircraft that are aging, and their fuel tanks are flaking. And the flakes come off and get clogged in the fuel line. And if you're a pilot of an airplane and you lose an engine because you've got fuel tanks clogging your fuel line, it is not a good airplane to be in. Lasers remove the mold release from molding plastic airplanes, the composite 787 aircraft. You build the skin, and when you remove the skin, you can't paint it, or you can't weld it, or you can't bond it. You need a laser to remove the surface layer of that mold release compound so you can use the material and fasten it to make an airplane. Lasers can clean jet engine turbine blades. So last week I was handed a jet engine turbine blade. And the moment I was handed this jet engine turbine blade, I said, I know the color of that dirt. That's the same color as the sky in Saudi Arabia during a desert sandstorm. Indeed, this was a jet turbine blade that had been on an aircraft flown in the desert in the Iraqi area. What had happened is they had flown through dust and dust storms, and that dust in the core of the engine melts, and it coats the blades. This blade had a coating about 1/8 of an inch thick on the blade, and that meant the engine performance is being compromised severely. Guess what? A laser can remove that material without harming the blades underneath. Is that valuable to you? You bet, because we're entering an era today when you can't just go buy the next generation aircraft. In fact, at the end of all wars, we've always had a problem where we had to rebuild our armament to make it work, and you do this often by rescuing and rebuilding what you used in the last war. Lasers can help you save your turbine blades, which means you can rebuild the engines and have them work again. If you want to laser depaint an airplane, here's a good example. A 5 kilowatt average power laser can depaint a 747 size aircraft in about 1 week. Most of it's automated. The laser arrives on a robot. And you do this in a completely eye-safe way in which there is the work on the aircraft doesn't have to be disrupted. You can continue to do other things. The laser creates a powder out of the paint. The powder is vacuumed up. There's no solution, no chemicals. It's a very environmentally safe way to deal with the airplane. Let me give you some examples. Here we are in the top of a high building in Philadelphia. So what's this man doing down here with this eagle? Zoom in a little closer. He's holding a laser. I can see it. There's a laser. What's it doing? It's removing all of the rust and all of the dirt that's been on the statue of this eagle and that's collected for the last 30 years. So he's not a technical person. He's not a laser jock. He's an artist. And he volunteered to use the laser to clean up this bronze statue of all the rust and garbage on it. So he laser depainted the statue over a period of a summer. The laser worked fine the entire summer. He loved the job. He thought it was a neat way to preserve artifacts that otherwise were being damaged by chemicals in the atmosphere. Lasers harden. So here's an article in the latest Aviation Week. Discretely formed 747-8 high wing loft is made stronger with lasers. So this is laser peening of the leading edge. Here are the various ways that you can selectively remove material from an aircraft surface. You can remove coatings, you can remove paint, you can even go to low observable surfaces and selectively remove down to a given layer. All right. So the Air Force has a number of aircraft that need fixing. And fixing means you can clean the jet engine turbines, you can clean helicopter blades that have been pinged or damaged, and you can do laser removal, paint removal for inspection of the aircraft. Those are all things that have been demonstrated that they work and work well. So here's a laser riding on a robot arm. This is a Sikorsky blade, a helicopter blade, and it's being stripped of its paint using the laser. There have been very careful measurements done to show that this composite helicopter blade does not reach any temperature high enough to do any damage to the underlying composite. So the heat is applied, the paint comes off, absorbs the laser and comes off, but the rest of the helicopter blade stays cool. What is this? Is a drawing on the wall of a little company in San Jose. Top coat, flex coat, gray specialty coating, primer, silver. Anybody know what that coating is? You guys are in the Air Force. You fly low observable aircraft. This is a diagram of a low observable coating. What's the problem with low observable aircraft? The guys that built them never thought about servicing them. They didn't give you a manual to tell you how to go through this coating and not destroy it, which would then hurt the low observability of that aircraft. So what do you need to worry about? You use color sensing and a Q-switch laser, and you go ahead and work. And you can selectively remove the layers of the observable coating down to the layer you want to get to, do your repair, and then rebuild the coating layer by layer back to the way it should be. So here's the head that does the work. It's a Q-switch fiber-delivered YAG laser. Here's the actual sample this is an inverted pyramid, layer by layer. It's stripped down to the silver layer. That's the silver layer down below. So here's a little bit of what you're seeing. So you work your way through the low observable coating down to this layer right there, and you've not touched it or damaged it. So after you've done what you need to do, you can rebuild this back up again. So that's a laser selective depainting of a very selective coating. Here's the more normal thing you would be asked to do. FAA came out 2 years ago and said, take your 737 aircraft and go inspect for cracks in the fuselage. So here is the laser handgun, the laser depainter, and it's removing paint on the aircraft near the overlap joint. We can take a closer look at that. Here's what you're trying to do. You're trying to get down to the cracks of that aircraft. And so the laser depainter does that. It's perfectly eye safe. The moment you lift this off of the aircraft skin, it shuts itself off, so there's no eye safety problem. And you can rather nicely remove only the paint and not touch the aluminum underneath, because the color recognition allows you to do that. So this process has been certified by the FAA now, called the GLC laser paint removal process, and Boeing Corporation has agreed that it can be used on all of their aluminum-skinned aircraft as a way of depainting their aircraft for inspection or for other operations. So this is the stealth utility being applied on aircraft in this country, and hopefully someday will be much more widely applied so that we can build the base of lasers. Because of the time, I think I'm going to stop there, and I'll just say the future directions are indeed interesting. We're working on laser-driven accelerators, which will lead us to coherent X-rays, and across the bay, our friends are building laser fusion engines, and they're trying to build 35 megawatt lasers to drive it. The future looks bright. The lasers are 50, but I think we have another 50 years to go with no trouble. Thank you very much.
So we have time for a question or two for Bob. So I'd be interested in just hearing a little bit about the future, if you might tell us.
Well, I have a quote there from Yogi Berra or from Bohr, right? It's difficult to make predictions, especially about the future. So my students have all known I'm pretty optimistic, and so they learned to take my predictions timeline and divide by pi, or multiply by pi, because I say you can do it in 3 years, and they find out it takes them 10. What's happening in the laser arena is that because the lasers are now 20% wall plug efficiency and they're marching toward 30% wall plug efficiency, it is realistic to talk about megawatt average power sources and applications of those. And we would not have even started the laser accelerator business if we didn't have an avenue toward lasers that can operate at megawatts at high efficiency. But our dream is to build a 1 meter long laser-driven accelerator and use that to drive an undulator to make a free electron laser at the 1 angstrom wavelength, or 8 keV wavelength. And the undulator is special. It's not a magnetic undulator. It's a dielectric undulator driven by mode-lock lasers. And it turns out that gives us more magnetic field and perfect control of the phasing so that our undulator is only this long. So a 1 meter laser driving a 10 centimeter undulator is a tabletop X-ray laser. And we've just been funded on that concept by DARPA just October 1st. So we've got 4 years of hard work to go to demonstrate the 1 meter long laser generating a gigavolt of electrons, and then 4 years after to build the coherent X-ray sources so we can begin to work with tabletop X-rays in our laboratory. So now if I remind all of you in what happened on April 10th, 2009. Anybody know? April 10th, 2009, a very important date. It's the date the world entered the coherent X-ray laser business. We are now in the coherent X-ray laser age. Did that impact any of you? I doubt it. You probably didn't even worry about it. That's exactly what the laser felt like in 1960. It was invented, but nobody cared because it didn't have applications at that point. The same is going on with the X-ray laser. Even though the X-ray laser at SLAC is oversubscribed for doing science, 200 proposals, 10 of which were accepted, it's not yet a tool that we know how to use. We will know how to use coherent X-rays now. We are entering the coherent X-ray age. So the future will be, 50 years from now, one of my academic great-grandsons or granddaughters will be here, and they will tell you about the latest, greatest thing that happened in X-ray science because they have coherent X-ray radiation.
Any other questions for Bob? Go ahead, Masoom.
How about heat? You have a certain efficiency you described here, and what is that? How do you take care of the heat generation?
Good question. So the question is, how do you take care of the heat generation in a laser, right? So when my students come to me and say they want to work on the next generation laser, I just ask them, do you have any experience being a plumber? Do you have any experience being an electrician? You've got to get power in, you've got to get power out. So in our way of thinking, we always try to remove the heat from the laser gain medium in a one-dimensional way. So then we can keep the wavefront of the light corrected. So that's slab laser technology or thin disk technology, or all one-dimensional cooled. And so we've learned how to do that quite well. And we've also learned that you want to keep all fluids away from any optical components at all. You want no coolant that flows anywhere near your optics. So we do conduction cooling. And we might use helium gas to help the conduction cooling. And with that simple rule, we know how to build lasers at scale rather nicely. The problem we face is materials. And so 2 years ago, we did a study for AFOSR on the research opportunities in scaling lasers to high pulse energy, high average power. And the bottom line of the community that did that study is materials, materials, materials. I need low loss gain materials. I need ceramics that can be scaled with low scatter loss. I need dielectric coatings that have higher reflectance and lower absorption loss. All of the elements came down to improved materials meant better laser performance.
So Bob, let me follow up on that question. You said you don't think that flowing coolant fluids is the right answer for high power lasers, but in fact most of the J-Hipsil solutions have some sort of flowing coolant in them. And is that
so flowing coolant is required to remove heat. I made the distinction. Flowing coolant in contact with your optics is not good. So I don't mind coolant over there, but I want to leave my optics in a very pristine, very clean environment with no fluid in contact with any optical surface. That's the statement I made. Okay. Now we have an example of a laser trying to be designed with, quote, flowing coolant between a set of thin glass sheets, halads, right? And I had dinner last night with one of the co-inventors of halads, just by luck, because in the same hotel. And we talked a little bit about it, and I just pointed out to him, I said, we've done lasers with coolant against the optics. They last about a week. The optics either damages or it gets etched, or the fluid creates index refraction fluctuations. Helium gas at 2 atmospheres is a very nice coolant, and it removes heat with no index refraction fluctuations because it's a very low index material. And we learned that lesson building lasers for the LIGO project, because LIGO lasers have to be quantum noise limited in phase and quantum noise limited in amplitude, a very, very tall order. And we found that the only way we could do that was to make conduction-cooled lasers where the heat was removed outside of the boundary of the optical material. Good question. Yes?
What's the value added for using lasers for accelerators?
The value added for using lasers for accelerators. The last accelerator that was designed on a global scale is called the International Linear Collider. And Barry Barish led the international community, and I know Barry well working on LIGO with him. And he's president of the American Physical Society this year. I'm president next year, so we meet all the time. So Barry chose the least risky technical approach to building the International Linear Collider, superconducting technology. The unfortunate choice in that down that path is that meant you needed a laser accelerator 30 kilometers long. Well, to build a machine 30 kilometers long is a $20 billion project. And there's no way in the world we live in today that you're going to spend that kind of money on physics. So you need a way to make the next generation accelerator on a scale that fits in the current laboratory environment. SLAC has a 3 kilometer long accelerator. Can I build a TeV scale machine in 3 kilometers? The answer is if I drive it with a laser. Because the laser brings with it 100 times higher gradient of acceleration. That's one. Number two, it allows us to run at a higher rep rate so we can control the machine. We want to run at 20 to 100 megahertz repetition rate, not 10 hertz. Right? And number three, it's more efficient. The calculations and the modeling we've done shows that with photonic band gap crystal structures, we can couple the electromagnetic field to the electron much more efficiently than the microwave sources that are built today. But the real key is cost. How do I get the cost out of the accelerator? What I do is I walk away from diamond-turned copper, and I go to the local fab shop that happens to be a lithography fabrication facility, and they build my accelerator on a chip, with lithography as the tool kit. So my students are busy right now making accelerator structures in our lithography facility and testing them at SLAC. Last week and this week we're right in the middle of a run testing some structures. So we will build lithography manufactured structures with diode pump solid state lasers and their cost performance numbers in an accelerator. The first one will be all of a few millimeters long, the next one will be a meter long, and then if we understand all of the hard things we have to learn, we might think about building a kilometer long accelerator to do TeV scale physics. A long answer to a very big question.
By the way, is it electrons and protons?
We can do electrons and positrons, but not we didn't design for protons. They're just too bloody slow and too massive. Right now, I'd be thrilled to build an electron accelerator. The electron comes out in 10 attosecond bunches, 100 nanometers diameter. I can put that through my dielectric undulator and have a coherent X-ray laser sitting on the tabletop. That's my dream, Mr.
Giant free electron laser.
A small free electron laser. So the giant one's at SLAC. SLAC has a kilometer-long accelerator and a 100-meter-long undulator. It works. And AFOSR sponsored the early work on FELs with John Nady way back in the mid-'70s. So those make coherent X-rays, and they're being built around the world, but they cost $500 million, $500 million each. Can we do X-ray lasers on the tabletop? And I think the answer is yes.
Okay, before we bring us to closure, I want to thank you, Bob, for coming and giving this talk. It was the inaugural in the series. And just as a small token of our appreciation, we actually have a 60th anniversary coin for the Air Force Office of Scientific Research.
All right.
Thank you very much.
Thank you.
And with that, thank you. Okay, so I guess that brings to closure our first seminar, and thank you very much for attending. The next one's actually in Dayton, Ohio. It'll be Sir John Pendry. I think it's in November. We'll have another one here in the D.C. area in December. We'll get that information out to everybody who attended today, and I'm not sure who that speaker is at the moment. Do we know? Okay. All right, so we'll get that information out. I don't remember who it is off the top of my head. So thank you very much for coming, and we appreciate it.
Thank you.
Thanks, Bob.